All right, so I wanted to do this example and use this example to illustrate how do you calculate electric field. And it's very, very similar to when we did forces. You still have to draw your vectors. You still have to find the magnitude. Still have to do components. Okay, so it's very similar. It's just now we're not looking at forces. So let me talk about this example. We have a point here, right here, point A. There's no charge at point A. It's just an empty point in space here. So what the question's asking is, what is the electric field at point A here? Okay, and just to give some numbers here, or give some references, I'm gonna call this charge 1, charge 2, and charge 3. Okay, so if I reference charge 2, you know what I'm talking about. All right, so what's the electric field at point A? So the first thing I'm gonna do is draw my electric fields. So let's draw my electric fields for, let's say, charge 1. What direction is the electric field going at point A from my 10 nanocoulomb charge? Well, it's a positive charge, so that means we had to draw the electric field going away from it. So my electric field for charge 1 will look something like this, E1. All right, what about charge 2? What direction is it going for charge 2? Well, charge 2 is a negative charge, so that means electric field points towards negative charges. So I'm going to draw my electric field like this. Oh, come on. E2. Like that. Okay, so there's my electric field for my negative charge for E2. And let's look, last one is charge 3. Well, again, that's a positive charge. So for positive charges, electric fields go away from that. So positive charge, draw my electric field like this, E3. Okay, so there are my electric fields. Next, we're gonna find the magnitudes. So to find the magnitude for the electric field for point charges in particular, try a little bit better. E equals KQ over R squared. That's our general equation for electric fields from point charges. Okay, so I'm going to draw it. Let me do this problem. So let's find E1. KQ1 over R1 squared. And let's plug in our numbers here. So K, I'm just going to put K, but it's that same constant that we did with Coulomb's law, right? 8.99 times 10 to the 9. Q1, charge for Q1 is at 10 nanocoulombs. Remember, nano is 10 times 10 to the negative 9. So make sure you put that in your calculators when you plug in. And then R squared, well, what distance are we talking about here? Well, we're talking about the distance between charge 1 and point A. This distance right here, which is the 2 centimeters. Oops. So 2 centimeters, 0.02. And I'm going to, nuts. I'm going to take these to be 2 sig figs. I hate when things are 1 sig fig. Okay, so I get my equation for my value for E1. Okay, so E1, plug that into my calculator, 8.99 times 10 to the 9, 10 nanocoulombs, so 10 times 10 to the negative 9. And then divided by centimeter, or 0.02 squared. Okay, how to convert that centimeters to meters there. Okay, and I get something kind of large, 2.25 times 10 to the 5. Okay, now what we haven't talked about are units. What is the unit for electric field? Well, remember how I defined electric field? F over Q, how much force you get per charge? Well, you use that for the units, newtons per coulomb. That's how much. That's my my unit for electric field, newtons per coulomb. Which kind of makes sense, right? It's how much force you get for every coulomb of charge that you would put there. This is essentially what that unit means. Okay, so there's E1. That's my electric field for the 10 nanocoulombs. Let's do E2. Whoops, make that a little bit neater. So E2 is K, the charge is 10. Now I'm not going to put negative there because I'm just finding magnitude with this equation. And then the R, what's the R distance? Well, the distance we're looking at here is the distance from this negative charge to point A, right? This distance here. So we're going to use Pythagorean theorem for this triangle, right? Or this triangle, it doesn't really matter, right? So if you use Pythagorean theorem to get the, well, I'm just going to write it out. So 0.02 squared plus 0.01 squared. Okay. So I do expect this number to be smaller because it's more distance. More distance means weaker electric field. And I get 0.02 squared plus 0.01 squared. 1.80 times 10 to the 5. Yeah. Newtons per coulomb. Okay, last one. So that's E1. I got E2. Let's do E3. E3, same equation. K, Q in this case is 5 nanocoulombs. And again, R squared. What distance are we looking at here? Well, the distance we're looking at is from this charge to our point of interest, right? This distance here, which would be the 1 centimeter. Okay, and we get our value. So 8.99 times 10 to the 9 times 5 e to the negative 9 divided by 0.01 squared. So we get 4. Well, I guess it's, if I round it to 3 sig figs, 4.50. Did I do that right? Yeah, looks right. 4.50 times 10 to the 5 newtons per coulomb. Okay, so I got E1, I got E2, and I got E3. Okay, now that's not quite what I'm asking, right? Because the question is, what's the magnitude and direction of the electric field at point A? Well, I know all these individual electric fields, right? E1, E2, and E3. I need to combine them now, and we're going to do vector addition for that. Okay, so I'm going to draw a quick axis here. And I'm going to just draw my electric fields I had. So I'll try to stick with the same colors I had before. So E2 is I had blue. Okay, so there's my E2. And then I have, what was the other one? E1 was in green. So E1 was going this way. And then I had, I think E2 was in red. Yeah. Or no, that was E3. Yeah, E3 was in red. All right, so E3. Okay, so at this point, we already did all the electricity magnetism stuff already, right? By using E equals KQ over R squared. That was this semester's physics. Now we just use our previous knowledge from our physics classes to add vectors together. Okay, so this is more review than anything. But we do need this angle. I forgot to get this angle here. All right, we're going to find components. We need that angle, which is not too hard. I could go back and show you. If you imagine that triangle that I mentioned earlier, all right, this triangle like this. You know what, let's do this triangle. Imagine that triangle. We could use that triangle to find the angle, in particular this angle, by doing tan inverse, right? Kind of like we did in a previous problem. So theta equals tan inverse of opposite over adjacent, so 1/2. Okay, so tan inverse of 1 over 2, what do we get there? 26.6 degrees. Okay, so that's what that angle is. Okay, so let's do our vectors. So I'm going to do x components, y components, and then I have E1, E2, and E3. Okay, so let's do E1. So E1 is pretty easy. You can see E1 is along the x-axis. So we know what that E1 we calculated to be 2.25 times 10 to the 5. Okay, so 2.25 times 10 to the 5. Okay, that's in our x direction. And for the y component, it's 0, right? Because it's only along the x-axis. E2. Now E2, it has an angle there, so we're going to have to use components, right? We're going to have to use sine and cosines. So to get the x component, let's see. To get the x component, the angle is adjacent to the x-axis, so we're going to use cosine there. What was E2? E2 was 1.8 times 10 to the 5. So it'd be 1.8 times 10 to the 5, and this is times cosine of my angle. Okay, 26.6. Now, it is in the second quadrant, right? E2. If it's in the second quadrant, that means you got to make this negative. Okay, let's get the y component. Y component would be 1.80 times 10 to the 5 sine of 26.6. Okay. And again, positive because it's in the second quadrant. So the y component is positive. And then E3. So E3 only on the y-axis. So E3 is not going to have an x component. It's 0. And we calculated for E3 4.5 times 10 to the 5. So 4.50 times 10 to the 5. Okay. And we add these up to get our net electric field. Okay. So E net, I could write it like this. So let me add up all my x components. So 2.25 times 10 to the 5. Minus the 1.8 times 10 to the 5 times cosine of that angle, 26.6. So I get 6.39. I mean, you got 6.40 because of rounding errors probably. 6.39 times 10 to the 4 newtons per coulomb, and that's in the x direction, right? So I'm gonna put this as I hat. I'm doing unit vector notation here. Plus my y component stuff. Oh, I forgot something for the y component. E3 is going downward, so this should be negative. Well, good thing I caught that before I did the calculation. Yeah, E3 is going down, so I have a negative y component. So for the y component, so 1.80 times 10 to the 5 times sine of my angle minus the 4.50 times 10 to the 5. And I get a negative 3.69 times 10 to the 5 newtons per coulomb, J hat. Okay, so there's that unit vector notation. Okay, so I put a unit vector notation because I can. And also, we can use that to find the angle and magnitude. So magnitudes, to find the magnitude, once you get that unit vector notation, all you got to do is take the square root of the E net x plus E net y squared. So E net x squared plus E net y squared, and we have our values there. The square root of the E net x squared plus the square root of the E net y squared. And I get, 3 points. And now this is where I'm going to keep it. This is my final answer, so I'm going to incorporate the sig figs in here. 3.7 times 10 to the 5 units per coulomb. And I get an angle. To get the angle, I do tan inverse of my E net Y over E net X. This will be the direction of my net electric field. So you can see here, so tan inverse of my E net Y over my E net X. 6.39 times 10 to the 4. Okay, so I get 80, pretty much 80 degrees there. Where is that 80 degrees? Well, if you look at the components here, positive X, negative Y. Well, what quadrant do you have that? Well, positive X, negative Y, that's a fourth quadrant. So my E net is somewhere down here. Whoopsie. Something like that. And that angle, the 80 degrees, we're looking at this angle here. Okay, between the x-axis. So 80 degrees, and I'll put below, see if I can fit it in here, positive x. All right, so just specifying where that angle is. All right, so this is our example here, is just to get us familiar with electric fields. Hopefully, we've done so far in the YouTube lectures, we've done 3 examples with vector addition, and that vector addition keeps coming up. Pretty soon, we're going to be starting chapter 23 really soon. Chapter 23, we're using vector addition, but with integrals. Okay, so it's really important to get this vector addition stuff down. If it's a little foggy to you, review this over and over again. Ask yourself, how did I get the cosine? Why did I use sine? And see if you could do these components on your own. All right, we are going to do, I have one more example for the electric fields, which is a little bit more analytical than numerical. So we'll be looking at that next time.